an introduction to rational functions. Recall that a rational number is any number that's being divided. So it's something divided, and that means that a rational function is a function, so some function n of x that's being divided by another function, d of x, let's say, where d of x can't be equal to 0. And that's the first restriction that we can talk about when we address the domain of a rational function. So the domain is restricted by the x values that make the denominator 0, that make the denominator 0. And so out to the side, this will be one of the first questions you'll ask yourself is, why does this restriction make sense? So let's talk about, and this isn't a question, it is a statement. So let's talk about different discontinuities, which are also restrictions on the graph of a rational function. We have two discontinuities that are listed here, and the first one is called an asymptote. You've seen this word before in Algebra 1, and an asymptote is a discontinuity in the graph, so it makes two parts where each part of the graph has some piece that approaches a line, and the asymptote is that line that the graph approaches. So there are three different kinds of asymptotes because there are three different kinds of lines. I misspelled approaches. So three different asymptotes for three different kinds of lines: a vertical line, a horizontal line, and a slant line. And in math, we sometimes call this an oblique asymptote as well. So a vertical line only goes through the x-axis, so this is an x equals equation. The horizontal line only goes through the y-axis, so it's y equals. And if you've got a slant, an oblique, diagonal line across the coordinate plane, we'll want to see this in y equals mx plus b, so we can graph it really easily. So let's look down on this learning activity we have here, and we'll talk about this other discontinuity that is the hole. So we've got asymptotes and we've got holes, and that just means we'll see a break in the graph, a break in the graph. So this break would be the hole in the graph. So a vertical asymptote. A vertical asymptote is a non-removable discontinuity. So it's non-removable because the asymptote occurs when there is something that x can't be, because it would make the denominator equal 0. So the denominator would equal 0. So x cannot be this value because the denominator cannot be 0. And it's non-removable because we can't get rid of the factor. And recall, a factor is something that's being multiplied. And we factor quadratic equations, right? Quadratic and cubic, quartic equations, those equations with a degree that are higher than 2, a degree greater than 2. So let's look at some examples of functions with vertical asymptotes. And we see here that these functions have something in common with the exponents between the numerator and the denominator. So that's something else that you can think about to yourself out to the side is what relationship could be made from these examples about exponents in the numerator and the denominator d of x. So we can think about that question as well as we factor these examples, because we'll need to factor those quadratic equations to see if we can get rid of the factors. So if we factor this first equation, we get 5 over x plus 1 times x minus 1, and there isn't a factor that cancels out. So both of these factors don't cancel out. The factors don't cancel out. There's not one up top, one on bottom. Well, they wouldn't cancel out. They would reduce, right, because they would equal 1. So there's a vertical asymptote at each of these points. So a vertical asymptote at x equals -1 and x equals +1, those vertical lines, and then the domain would be the value of x that makes these 0. So x can't equal -1 and x can't equal +1. So I'll leave you to do these two examples. See if you can find factors that cancel out as opposed, or factors that can't cancel out or get rid of, as opposed to wholes where we can remove the factor. So wholes are a removable discontinuity because we can remove the factor. And I'm going to change this to remove or reduce, and think about why I changed this vocabulary as we look at if we can factor and cancel out any factors of these examples of functions. So let's look at these examples, and I see if I factor the denominator, we have x plus 2 and x minus 2, and the x plus 2 cancels out, which means we have a horizontal asymptote at this line, x equals -2. So then the other asymptote would be that factor that doesn't cancel out, a vertical asymptote at x equals 2, and then the domain are the values of x is restricted by these values of x that make the denominator 0. X equals -2 and x equals +2. And so you can do the other examples in here. So basically, as you've noticed, if it crosses out, then it means there's a hole in the graph. And if it doesn't cross out, then that means there's a vertical asymptote in the graph.